Okay, so I hope you can all hear me fine. My talk is going to be on applying complexity science to building blockchain economies. So over the past few decades, with the rise of information technology and the internet, and particularly now with the emergence of the decentralized web, we've started to build these new forms of institutions, these new forms of networked organizations. They take very different form, different dynamics to the ones we know from the industrial age. My argument in this talk, and what I'm going to try and give an overview to, is how we can apply or bring the ideas from complexity theory, complexity science, to bear on trying to understand, model, analyze, design, and develop these new forms of organizations, and how we really, if we want to build these kind of large decentralized networks that blockchain, token economics, and so forth offers us the possibility to do. If you want to do that in a sustainable, effective way, we really need to bring these ideas to bear on doing that. So, what is complexity science? I'm going to give an overview to complexity science first, a kind of introduction, a crash course, quickly, and then we're going to talk about how it relates to this world of decentralized technologies. So what is complexity science? Many different definitions. Maybe the easiest one is simply as the science of complex systems. So it's the study of these things that we call complex systems. What is a complex system? It's a system that's composed of many parts. Those parts are autonomous, interconnected, and interdependent. So take any complex system and you'll see that it has many small little parts that are distributed out. So this flock of birds is a good example, an often cited example. And it kind of gets the essence of what we're studying in complex systems. We have all these little parts, they're spread out, there's no centralized coordination. We're asking how, through local interactions, we get the emergence of a global pattern of organization. And there's not only do we have many parts, but those parts are also autonomous. They're in some way independent. They're making decisions, or they're acting based upon their own logic and the information they receive locally. So again, there's no centralized component coordinating the whole system. Every actor has some influence in the system and gets to a certain extent to make their own decisions about how they're acting. Like that in that flock of birds, each bird is responding to the local information it's receiving, has its own algorithm, own logic about how it's going to act. The society is another good example of a complex system. Each member in the society has a degree of autonomy, a degree of adaptive capacity, and that the result of that is that we get some degree of diversity in the system, right? Because people can actually respond to the local information. That means they can respond in different ways, and we can get kind of diversity in the system. So many parts, those parts are in some way autonomous. There's no centralized control, and they're highly interconnected. All the parts are highly interconnected, and that creates like a network structure. So a transport system is a good example. Not only are they interconnected, but they're also interdependent. Big idea in complexity theory, interdependence. So an ecosystem is a good example of that. An ecosystem is a complex system. Many different parts. Those parts are autonomous, and they're interconnected, but they're also interdependent, right? If we change the acidity in this water here, this lake, or if we did away with one of the species, or if the coral died or something, that would affect other species, and ultimately it would affect the whole system. So nothing kind of happens in isolation in these systems. Everything is to some degree interconnected. So those are kind of the properties of complex system. When you see a system that has those properties, you can say it's a complex system. But you might ask, why do we need like a new kind of science to study complexity, to study systems that are like that? The answer to that is that the scientific framework we've developed over the past 400 years since the beginning of the modern era turns out to be based upon a set of assumptions that only really hold for simpler systems, right? Systems that have fewer parts, that aren't so highly interconnected or interdependent. And we call that kind of framework, those set of assumptions, the way that traditional science works, we call that reductionism or analytical reductionism. And it turns out that doesn't really work for when we're dealing with complex systems. We first saw that when we were trying to study, weather patterns and chaos theory that emerged out of that in the 70s. That was the first big introduction to this new world of complex systems. We saw that those assumptions underlying modern science kind of broke down. We needed new assumptions when studying these complex systems. So over the past few decades, we've seen the emergence of a number of different models from different areas that have kind of combined and come together to give us a general framework for studying complex systems, and we call that complexity science. And it turns out to be very different to our traditional approach to science. And what are some of these dynamics, these features, these complex systems that don't really fit within our traditional way of looking at the world? And the first one is really this idea of emergence, but also self-organization, non-linearity, and evolution. These are kind of the main features that when we look at complex systems, these are kind of the main dynamics and features that pop out of this, and we really want to kind of understand. So emergence is kind of the big idea. It's the idea that all the parts are some way different to the whole system. So life is a good example. This little plant here, it's a living system, but if we broke that down, like if we took it into the lab and we kept on taking it apart, did reductionism on it, we'd find that at the end of the day it's just made of carbon molecules, and those carbon molecules obviously aren't alive in themselves. But when we put them all together in a particular way, we get the emergence of a living system. So we can see there like two qualitatively different levels, these kind of inanimate molecules on one level, but on another level, when we put them together in the right way, we get this animate, this living system, the plant. So that's emergence. And we see that in all complex systems. It creates two different levels, and those two different levels really create a lot of the complexity that we're thinking about. The human brain is a good example, often cited example. Billions of neurons, trillions of synapses, connected in a particular way to create ideas, emotions, consciousness, and so forth, which itself is very, very different from those simple, the operations of those very simple binary switches that are neurons. So we see it a lot in society. When we put people together, we get organizations, we get dynamics that are qualitatively different from the individual people. And the second idea that really fascinates people is self-organization. There's no centralized control, as mentioned. So how do we actually get order in these systems at all? Like, would it not just be a kind of chaotic mess if no one was in control? That's our kind of traditional assumption, that we need to impose order on the system. But that's not really what we see in these kind of distributed complex systems, like a school of fish or that flock of birds. Actually, they turn out to be quite organized in many ways. They're not random at all. They're a bit messy, but they're definitely not random. And that comes from this idea of self-organization. It's not really an idea, it's more of a kind of theory or a set of models about how parts interact through only local interactions. We can get specific dynamics that create overall coordination within the system, as we can see in this school of fish, or we saw in that flock of birds. Yeah, and ant colonies, ants, a very good example of that. There's no master ant telling all the other ants what to do. Same in a beehive, the queen doesn't tell all the other bees what to do. It's actually only through local interactions, so the ants leave pheromone trails that tell other ants what to do, and there's positive feedback that creates attractors and emergence. I won't go into all of that now. This is, again, just a quick overview. You could dig right into any of these topics. I think we produce a course on pretty much every one of them, so it's like a whole subject in itself. Non-linearity, another big idea, particularly nonlinear dynamics. That's a lot of where complexity theory came from. Chaos theory, and really the central idea there is feedback loops over time. So we get effects kind of feeding back on themselves and amplifying themselves, like compound interest. More of A feeds through to create more of B, and B feeds back to A, and this builds upon itself until we get exponential change. So it's like network effects, like in languages or the adoption of a new technology like a mobile phone. More people that are using it, the more valuable it becomes, so more people use it, and you get exponential change. And that's what we see in complex systems. They can change very rapidly. So they have periods of linear growth, but then you get these really rapid, what we call phase transitions. You get that tipping point and feedback kicks in, positive feedback kicks in, and the system very rapidly changes. And it can degrade, or it can, go up to another level through that feedback loop. So the network effects adoption of like mobile phone, that's kind of a creative process, should we say. Whereas a financial crisis, it's the same dynamics, exponential change and feedback, but it's happening in the opposite direction, leading to systems crash, like ecosystems collapse. Those things happen very rapidly because of this feedback. Network science, network theory, another big area of complexity theory. As I said, all complex systems highly interconnected. Those interconnections create a network structure in the system. That network actually comes to define a lot of how the system is working. So it's no longer, once you get high levels of interconnectivity, it's no longer so much how the parts, the properties of the parts, it becomes a structure of the network. So if you look at this network, it could be a financial network, could be a transport network, could be, a communications network or a social network, should we say. And if you're there in the center, one of those central nodes, you're going to have, you're going to live in a very different world, really, to the ones living out on the edges. You're going to be getting different information. You're going to be getting more information, and that's going to kind of shape the context within which you exist, and it's going to shape, how you behave, the properties of the parts, should we say. So, in all complex systems, to really understand them, you have to study them from all of these different perspectives, but certainly from the perspective of network theory, and understand the architecture of that network. So evolution is another big idea. It really describes how complex adaptive systems change over time. So like I said, when there's no centralized component, no one defining, how the system is going to behave or imposing order on the system, then that means there's no one kind of defining the future trajectory of the system. Right? There's no CEO like at the top of a corporation who says, right, we're going to do this, we're going to go in this direction or whatever. In these adaptive complex systems, it's actually all about the local interactions and the way the component parts are adapting and reacting to each other's behavior. And the kind of long-term trajectory of a large complex adaptive system is defined by this idea of evolution. So it's not just an ecosystem. Obviously, we came up with that idea first in natural selection, but now complexity theory generalizes that to any complex adaptive system. So it can be a financial system, it can be an economy, it could be a whole society, or how, the evolution of culture over a prolonged period of time, over thousands of years, or even civilization. But here is a very good concrete example. This lady standing in front of this selection of products. We can see here the basic dynamics of how evolution is working, right? Those components are the production of variety, selection, and duplication. So what's happening here is the supermarket or a number of producers have created different products, and they didn't know which of those products would really work or which ones she would want and other consumers would want. They produce them, they put them out there in front of her, and she comes along and she asks which ones are suited to what I want. To my particular context, she chooses it. In so doing, she performs selection on that variety of products. And then, of course, she's not the only one doing it, right? There's thousands, there's millions of other people in the economy performing selection. And that information that they give about which ones are best suited to that environment, which products, that is sent back to the producers who created the variety in the beginning. And they say, okay, these products are not needed, these ones are obviously a good fit for the market, so we'll produce more of those, we'll stock more of those, we'll put more of them on the shelf. And in that way, certain products die out, certain companies die out, and others become more prominent. They're kind of duplicated, right? They produce more of those products. Those companies get wealthier, they become more prominent in the economy. And as a function of that, the whole economy changes over time through that process of variety, production, selection, duplication, that is evolution, and that can be seen in all complex adaptive systems. So that's pretty abstract theory about how complex systems in general work, all kinds of complex systems. And we might ask, why would we care about that very abstract knowledge? And my argument would be that we should care about it because the world has just become a whole pile more complex just in the past few decades. If we look around ourselves now, we really find ourselves embedded within these very complex global networks, right? So if you look at where your media, where your money or your car or your shoes or your phone, where they came from, well, they were produced by this, these incredibly complex global networks, complex supply chains. Right? If you look at your phone, it says it's made by Samsung or Apple. Well, it's not really, right? They just designed it. In fact, it was made by, a huge network of companies around the planet that were taking resources maybe out of Africa and, producing it in China or somewhere. It's designed somewhere else, and someone else was financing it, and so on. And that's kind of the reality of the world we live in. Since kind of the rise of globalization and information technology, those have really been the key drivers, the expansion of the global market system, supply chains and finance, coupled with the rise of information technology. And that's really kind of, with those, the connectivity has proliferated massively. We now call that hyperconnectivity. We have more nodes. There's a greater number of connections between those nodes and greater exchange of information, of resources, of finance and so forth. And that's complexity, right? It's kind of the world we live in now. And we need to respond to that in some way. Because those complex global networks, they produce all these good things, right? Our phone and our computer and so forth. But they also produce, these bad things that we don't really want, these wicked problems, we call them. And we can give many examples of those. Global cybersecurity, I would say, is one example. That wasn't such a problem just 40 years ago. And now it's a serious problem, and going forward, it's going to be a really big one. But, many forms of environmental degradation, soil erosion, like in this picture. And it's really this global market economy that's producing those. And the institutional systems we developed over the past few hundred years, centralized hierarchical systems, they really can't respond to that kind of complexity. And in the face of it, they're really stalling. They're not providing the solutions we need. A lot of how our world kind of operates now, I mean, we talk about these global networks, supply chain, finance, and so on. Well, that's really about the global market system. And that's creates a lot of things we want, right? But it's also creating those other things too. And that's because of the way it's kind of incentivizing us. The market system is a lot about incentives, and it's incentivizing us as individuals, as companies, to perform certain actions that have negative externalities. And those externalities we see kind of build up over time, the little negative externalities that we create as individuals, the way we're incentivized to overconsume, or we're incentivized to, jump in our car. We can see that here. All right, we're each incentivized to take a little journey in our car, but we know that creates a little negative externality, and that adds up on the global level and creates a kind of systemic crisis, systemic instability, and these macro scale problems that we don't have solutions to. And that's part of how we're incentivized to act. So like plastic pollution would be another example. Companies are producing all this plastic, and we're using it, and we're not really paying the full price for that. We call that the tragedy of the commons, right? Negative externalities that are not being accounted for. Another good example is, in finance. How did we get that financial crisis? We got it because these traders were incentivized to produce products, these toxic products, that had small negative externalities. And over time, those accumulated, built up in the market, and eventually we got systemic failure and a crisis. That's tragedy of the commons, and we see that behind many of these kind of wicked problems that we live with today. How do we deal with that normally? We impose the top-down solution, governments, regulation, and that worked fine. That worked kind of fine on the national level, but now, of course, we live in this world of complexity, of global networks, and that's not really working on that level, right? Those kind of institutions, they aren't designed for that level of complexity, and they're national anyway. We haven't been able to build kind of global top-down institutions, and nobody really wants them. So that's a big problem, and this talks about the rise of networks, and my argument is that really to figure out how to manage or coordinate that kind of global market system in a way that moves towards sustainable results and doesn't create these negative externalities, we can't do that by kind of imposing it in an external way. as we have done in the past, right? So in the past, we solved all those problems by kind of getting the government to regulate everything. You know, if we had inequality, we'd just take money from some people and give it to others. If we had environmental problems, we just, you know, go in and put regulation. We can't really do that on the global level, and that's why we get a lot of these problems. And to actually solve those problems, we actually have to build it into these kind of market structures. We have to refactor it into it. And the rise of networks is really the kind of the story of our age, isn't it? The market system is really a network, but also information technology. So Gary Hamilton puts it well here. For thousands of years, markets and hierarchies were the only alternative when it came to aggregating human effort. Now there's a third option, real-time distributed networks. And there's been some studies on this, the rise of networks over the past 50, 70 years. Yochai Benkler from Harvard Law School, he looks at this evolution of networks through from the kind of traditional hierarchy back in the mid-20th century, where everything kind of well accepted that everything had to be done in the hierarchical fashion, through to, you know, the rise of the market system, which is kind of a decentralized market, a decentralized system to a certain extent, to the rise of online platforms, the internet, and now we're moving into this next generation of web technologies where we're really going decentralized token economies. So decentralized systems, that's kind of what's in front of us now. I think this audience all understands what blockchains are and token economies are, so I'm not going to dig into that here. But for me, I mean, the kind of fascinating thing is that this technology, this next generation decentralized web, token economies, they kind of emerge, those two really powerful driving forces in our world. The expansion of the global market system and the expansion of telecommunications, information technology. And they kind of integrate the two in new ways, in very kind of surprising, like we really didn't expect that to happen. And they integrate them in kind of powerful and surprising new ways, so that now, in a way, we're kind of bypassing a lot of, I mean, token networks and blockchain. They just kind of happen directly through the internet, right? Creating these decentralized networks, and they bypass a lot of the traditional institutions we built for incentivizing people, right? And that's kind of the big idea here, that now we can actually incentivize people directly, kind of through these protocols and directly to these mobile phones that everyone holds in their hand and they're kind of staring at all the time. And that is, that I would argue, is a very kind of powerful technology. And what we can do with it is harness it to try and incentivize people in new ways to create, instead of creating negative externalities, we can start to think about how to use these tokens, how to use these decentralized networks to get positive externalities and get emergence, right? Instead of the emergence of kind of negative externalities, the emergence of these systemic problems and failures, we can try to get the emergence of positive externalities and self-organization in a way, new levels of organization on the macro level. Yeah, I can't go into all the details here. This is a whole other story, but tokens allow us to quantify new forms of value, so we can create new forms of economy, and we can start to account for all the factors involved, all the costs involved, so that we don't get those negative externalities. So we're actually factoring in, the costs to the ecosystem when we produce a plastic bag or whatever, and we can incorporate that into, the economy and into the token, into the network, so that people are incentivized to make the right decisions, not just for themselves, but also for the overall system that they form part of. And that's not just in the environment, that's also social capital, that's cultural capital, and so on. That's a whole other story. It would take a long time to dig into that. But to give a quick example, we can think about, the consumption of fast food and healthcare. So at the moment, companies and individuals are incentivized to produce kind of poor quality food because it's cheap for the companies to produce, and because it taps into a kind of primordial biochemical drives for fatty and sweet food. So we're incentivized to consume low quality food, but we know, of course, that has a negative effect on our health, which has negative externalities and builds up to a really big healthcare bill, for example, in the US, but that's going to be the case in a few years in China also. Little negative externalities, the way we're incentivized, creates little negative externalities that accumulate and create systemic problems. And we can think about here creating a token to incentivize people to eat healthy food. So at the moment, the US, pays billions of dollars to mop up the kind of negative externalities of this stuff. But imagine if we just took that billions of dollars and we tokenized it, and then we incentivized people directly, saying, look, you can earn tokens if you eat the healthy food, right? Which is almost, it's almost like earning money, because there's $1 billion there, there's a few $1 billion there, to incentivize them to eat healthy food. And if you do that, of course, what you're actually doing is bypassing that whole kind of loop of them eating poor food and going to hospital and all the expenses and everything. We're incentivizing them directly to be healthy. So it's like you're just cutting out a massive amount of wasted, money, time, energy in the system. And that's just a small example of the power of incentives and how you can use tokens to kind of incentivize people towards positive externalities and get the emergence of kind of sustainable solutions. And I think this is really key to sustainability. I don't think we're going to achieve sustainability by the UN or some government kind of imposing carbon taxes and so forth. We're going to get it by building these decentralized economies that work, that incentivize people to have positive externalities and the emergence of sustainable solutions. So that brings us to designing decentralized systems. All of what I said sounds very nice, but of course the problem with it is complexity. It's not simple. We built those centralized organizations. We do centralized coordination and regulation because it's relatively simple. That's one of the main reasons why we do it. And we don't do these decentralized systems because of complexity. We don't really know how to do them. We don't really know how to deal with that complexity, and that's why we need these ideas from complexity theory. We need to bring them to bear on kind of changing our way of looking at the world first, I guess, so that we can see things in a different way. And when you do, then you start to see new possibilities. You see how you can use this technology to enable new solutions. And I guess the main story there is, as I said before, that complex systems are very different from simple systems. And all our knowledge to date is really based around this assumptions of simpler systems. And that's why we've built a lot of institutions that are based on those same premises, when increasingly the world is very complex. And we need to learn how to harness that complexity instead of fighting against it. And of course, we need to understand the world in different ways if we're going to do that. So in terms of actually building these new kind of economies and networks, we need to take those original ideas from complexity theory as kind of guiding principles, should we say, about how we go about building these things. So the original one was emergence. How does that apply in this context? We understand it kind of in the flock of birds, but you can also apply that same concept in the design of a system, of a network, or managing an organization. So, I mean, David Snowden gives a good presentation of how it's not, when we go from the complexity paradigm, when we go into the complexity paradigm, we switch from kind of imposing order on the system to creating the context within which that order might emerge. So yeah, when you apply that to actually designing of systems, of economies and organizations, it's really about, instead of specifying outcomes, you're creating the context. You're giving them the tools to enable them towards self-organization. He gives the example, David Snowden gives the example of a child's birthday party. So if you think about organizing a birthday party, you're not really, that centralized kind of command and control approach is not really how you do it. You don't specify, every person who's going to be a part of it, every role that they're going to take, every single action and so forth, and you create a chart about what outcomes you want from it and so forth. That's not how it works, is it? You think a good child's party would be about just inviting all the children, and actually you're just creating the context. You're putting a lot of toys out there, maybe a little football pitch or a basketball court, or lots of food and so on, and you're really creating the context. And the children join, they interact, they play with toys, and we get the emergence of a child's party. children having fun and doing what they're supposed to do. And that's, kind of understanding how that works is, again, this idea of self-organization. And that really starts with getting rid of kind of specifying outcomes and providing the system with information, peer interactivity, peer connectivity. And it's only with that peer connectivity that you can get self-organization. As long as you have it kind of held in a specific configuration, you can't get the emergence of order from the bottom up. So you're trying to provide connectivity and information through which people can interact locally, peer-to-peer, and then self-organize. And a big part of that is feedback loops. If we're talking about designing token economies, really what we're trying to do is take like something that's managed in a centralized way and put it into a market. Token economy is a market, and you're trying to use that market to manage whatever the value is in that system, and you're doing it through a token where people are exchanging value as producers and consumers. And you're trying to close a feedback loop, really, like I was saying about externalities. An externality, a negative externality, is just a kind of broken feedback loop. Something's not actually really being paid for. And when you're designing these token economies, you're trying to factor in all the value that's being produced and consumed in the system so as to make it a self-sustaining system. And that's a feedback loop, a balancing feedback loop. Sustainable, resilient systems are ones that have many of those balancing negative feedback loops. Network theory is something we're really going to have to bring to bear in the design of these systems, because obviously, blockchains, token economies, they are networks, they are decentralized networks. To date, we haven't really, explored that very much. Actually, the only real idea from complexity theory that we're using is game theory, right? That's really popular. But going forward, we're really going to have to start using network theory and network science. There's 60 years of mathematics in graph theory now, and we could bring that to bear to understanding these networks much better. And I think that's already what's happening with the third generation of blockchains. You look at like acyclical directed graphs. Well, they're graphs, they're networks, and people are starting to bring network theory into the equation here. Evolutionary algorithms, so these are decentralized systems. They're going to evolve over time through selection, like in the market we saw how people are choosing where to put their value, their tokens, what they're choosing to invest in. Those become more prevalent in the system. Prediction markets are another good example. But there's a whole pile of evolutionary algorithms, and we can use those also. So just to wrap up then, I think we're in a technology revolution that's really only comparable to the industrial revolution or the agrarian revolution. And really the key technologies, I think, here are data analytics and blockchain networks, at least at the moment. And both of those technologies, they're different from the industrial technologies in that they don't just kind of change the world around us. They actually change us, right? Analytics changes how we make decisions. And blockchain really changes how we organize ourselves. So we can now create these large decentralized networks. We don't have to do everything in centralized systems. And that changing ourselves has a very powerful effect, because it really changes everything we do, everything we make, the world around us. And if we do it well, if we create, if we can actually design the right kind of incentives, the right kind of economies that factor in all the value involved, all the elements, all the parameters in the equation, then we can start to try and get positive emergence instead of negative emergence, and really start to make ground on some of these complex global challenges. And doing that, again, goes back to the idea of complexity and harnessing this complexity. Building these decentralized networks is really going to require that we figure out how to use all of this connectivity that has proliferated. At the moment, we're really just kind of pushing back against it, and that's creating a whole pile of friction. We're kind of continuing on with this centralized linear model that is kind of creating a huge amount of friction in a world of hyperconnectivity. And we need to start building institutions that are actually able to harness that complexity. And those are decentralized networks. And I think key to building that decentralized world is getting all these ideas from complexity science, complexity theory, and using them in the design of these networked organizations. Okay, that's pretty much it. Thank you very much.